Bismillahirrahmanirrahim. Students, today we have to try to solve the numerical problems uh, for Brayton cycle. So first of all, we are considering a simple ideal Brayton cycle. Statement of the problem is a gas turbine power plant operating on an ideal Brayton cycle has a pressure ratio of 8. So what does it mean? It's mean the pressure ratio, because it is ideal, so this pressure is constant. This pressure P2 and P3 are constant, P1 and P4 are constant. Pressure ratio mean P2 over P1 or P3 over P4. So we can write like pressure ratio P2 over P1 is equal to P3 over P4, and it is equal to 8. It is pressure ratio, and it is also represented by RP, pressure ratio. The gas temperature is 300 at the compressor inlet, because this is compressor inlet, and at this point A, temperature is 300 Kelvin and 1300 Kelvin, and at inlet of turbine, this is turbine, inlet of turbine is this one, so this temperature is 1300 Kelvin. So this is 300 Kelvin, it is 1300 Kelvin. Using a standard assumption, so working fluid is air mentioned here. We have to determine the gas temperature at the exit of compressor. So at the exit of compressor, it will be T2. So we have to determine T2 according to this diagram, TS diagram. This and exit of turbine mean T4. So T2 and T4 we have to determine. The back work ratio. Back work ratio basically is the ratio of compressor work divided by turbine work. So back work ratio, it is represented by RBW, and it is equal to compressor work, W compressor, and it is input, and W turbine, that is output. So we have to determine this, and further this compressor work will be H2 minus H1. So we can write like it will be further equal to H2 minus H1 divided by W turbine mean H3 minus H4. Remember, as we are farther from the origin, the enthalpy increases. So keeping this point in mind, if we are farther from the origin and that point is 3, this, so at this 3 there will be maximum enthalpy, and you can confirm it by while solving the problem. And minimum enthalpy will be H1 here. So we have to determine this. So if we know H2, H1, H3, H4, we can find the thermal efficiency. Thermal efficiency is, what is thermal efficiency? In case of Brayton cycle, thermal efficiency, generally thermal efficiency is W net divided by Q in. This is the a universal formula whenever you are dealing with the thermodynamic cycles. W net, the net work output, divided by heat supplied, Q in. So W net will be equal to, here W net will be the turbine work minus compressor work. So I can write here W turbine minus W compressor divided by Q in. If you look at this TS diagram, Q in clearly H3 minus H2. So we can write denominator can easily write as H3 minus H2. And what about W turbine? W turbine we have, and I have already told you, W turbine H3 minus H4. So basically it will be H3 minus H4 minus compressor work, and compressor work was input because compressor take the input power, h2 minus h1, so it will be h2 minus h1. So here this was part C and this was part B. Part C and B you can easily determine if you have h1, h2, h3, h4. So if you have these things you can determine. So then question rise, how we can determine the T2. Here we know there is a pressure ratio. Pressure ratio means P2 or P1. Fine. So we know T1. So we can start from here. T1 we know, that is, I am solving for T2. So T1 we know, that is 300. So if we know this, what table tell us? Remember, we have to look in the air table, not in the steam table, because here working fluid is air. So this is table A17 and I am using Unisanjal 9th edition, so its page number is 908. A17 on A17 we have to temperature is 300, so this is 300, this one 300, and we have H 300.19. so H we know, so against this temperature what will be the H? That will be 300.19 kilojoule per kg. Fine. Then again coming to second entry is PR. PR actually the relative pressure. So PR is PR1 because it is at state 1 is 1.386. 1.386. And remember this PR, what is PR? If you go at the bottom line here, the properties PR relative pressure and VR relative specific volume are dimensionless quantities used in the analysis. So these are used in the analysis of isentropic process, and you should not be confused with the properties pressure and specific volume. So PR and VR are relative pressure and relative specific volume we use in the analysis. So now we have this one. And another thing is we know the RPR pressure ratio. So according to that, PR2 over PR1 should be equal to P2 over P1. And remember this P2 over P1 is 8. PR we have just calculated. So PR2 will be 1.386. When you multiply by this, it will be 11 point something. So if I calculate this 1.386 into 8, so basically it is 11.088. 11.088. So again we should look at the table this pressure. So 11 point here, if you look at this 11 point approximately 11.1. so 11.1 relative pressure lies in temperature 540. So we can say, if you know this pressure by looking in the table A17, T2 is 540 Kelvin. So you can determine this temperature easily, T2. Then we have to also determine this temperature T4. We know T3, so same story. Against T3 1300 you have to find the relative pressure 1300 is here. So against this 330.9 is the PR. So when you solve When you solve for T4, T3 is 1300 against this PR2 you have. And when you have this temperature H3, now you can determine from the table. Okay, PR3 is PR3 from table is it is 330.9. 330.9. Fine. So again, same story. PR4, PR3 or PR4 equal to P3 or P4, and P3 or P4 is 8. So PR3, we know PR3, so we can put the value of this PR instead of PR3. You can put the value of this, and this value is 330.9, and here PR4. Now you can determine the PR4. Basically that is the 330 divided by 8. 330.9 divided by 8, it is 41.36 for 36.36, sorry, 41 point, sorry, it is 41.3625. So against this you can determine again, look in the 41 point something. So here you, if you look at this, we have 760 39 and 780 43 point something. So in between, by doing the interpolation between these quantities, 760 and 780, 760 and 780, you can determine the temperature. So how you will do the interpolation, I'm just showing in this lecture how to do this. So for that I'm just zooming it. Actually what we are doing, we know the pressure here. So intermediate pressure is lies, look at this, this is 41.3625, 41.3625, and here it is x. So what we do, we will x minus 760 divided by 780 minus 760. So we are subtracting first term from x as well as from. So same scenario, same pattern we have to follow here. This 41.3625 minus 39.327, the first term, divided by 4335 minus 39.27. So you can calculate x here, and I can calculate x for you and calculate it for you. So what are we doing? Actually, if you solve it, just keeping in mind, so very shortly I can write 760 because it is negative, so here it will be positive plus, this was 20 is multiplied by this, fine. So and then we can add 760. So basically this will be 760 plus 20 into bracket 41.3625 minus 39.27 divided by 43.35 minus 39.27. I have calculated it. overall answer is 770.257. Fine. So we can roughly say 770 Kelvin is temperature, and this is T4. So I can write here. I was solving here. So T4 means this after interpolation. T4 was 770.257 Kelvin. So now this problem is solved. So similarly, you can solve other problems. So if we move uh, H1, we know this was H1 against this temperature. So similarly, you can look the stream table and find the at this temperature what is H2, what is H3 you can find, and what is H4 you can find easily. Put the values here and get the answer. Then second example, that is actually the extension of previous example. In this example, we have to assuming a compressor efficiency of 80% and turbine efficiency of 85%, determine back work ratio, thermal efficiency, turbine exit temperature of gas turbine discussed in example. So the procedure how to find the back work ratio I have explained in the previous example. Value now will be different, but what will be the procedure that I have just explained. What is the value of thermal efficiency I have just explained, and how we can find the exit temperature of that I have explained. The main thing here that is different from the previous example is we are considering the compressor efficiency and turbine efficiency. So for compressor efficiency, if ideally that was isentropically ideally that was Ws, and that was H2 minus H2S minus H1, we have to divide it by the efficiency so that input power will be larger than the previous it was 244. Now we have to input power to the compressor 350. So what we have to do, just previous work divide by this efficiency will be the now new work after considering the efficiency of compressor. Fine. For you I can just write again. Previously, isentropically speaking, compressor efficiency was, this is for compressor, as for isentropic, that was H2S minus H1. Fine. But now we have to consider the efficiency, compressor efficiency. We have to include the effect of this efficiency. What we will do, we will just divide this by efficiency of compressor. And whenever it is turbine, you have to multiply the efficiency with the isentropic work. In case of compressor, you have to divide. In case of turbine, you have to multiply. Just this was new thing. So when you divide it, this will be 305. When you multiply by this Ws, so Ws in the previous case, if you look at this while solving, that is a turbine H3 minus H4, and this was 606. I have written here this is turbine H3 minus H4 ideally. So taking that into account and multiplying with 0.85, so this will be the 515. So what has been done, we have to give more power and we are extracting less power, so backward ratio will be higher than the previous. So we have to take the ratio of this W compressor or W turbine out. So it is 59. Previously it was very less. Previously it was 40%. Now it has increased to 52%. 59.2%. So what will be the we have to determine this efficiency H2A. So again, just apply the formula of this uh, efficiency formula are more easily. What is the this is the value of compressor in, and basically this is now this is the actual. So H2A minus H1, that is 305. So H1 you know, H2A you can determine. I'm saying I can write here H2A minus H1. Basically this is compressor work in after including the efficiency of compressor. So here H1 we know, this we know, this we know. So H2A you can determine. Similarly for turbine you can determine, and if you have the H, so uh, you can have the temperature against this value. Similarly Q in H3 minus H2A, because now it is the Q in, so that is 790, and W net, W out minus W in, basically difference between these two terms, that is we are using in producing the electricity, it is 210. So if you calculate the efficiency now, W net or Q in, so it is 26.6%. Previously it was much larger. In ideal case it was 44%, 42.6%, 42.6%, and now it is much less, much less than this 26.6%. H4A, it is similarly, you can determine H4A similarly as in the case of turbine, like by keeping this diagram in mind. Actually it is H3 minus H4A, so H4A can find from here, and when you have the H4A, against that you can find the temperature. So this is the way how to solve the numerical problems. So similarly you can in the next question we have this diagram. Just one thing is new, and that is H5. So how to determine the H5? Effectiveness is defined as H5 minus H2A. Actually that we have saved divided by the available was H4A minus H2A, and that was total available energy in the exhaust, and what we have extracted from this, that is H5 minus H2A. So effectiveness will be defined as a ratio of these both things, H5 minus H2A, that we have utilized, we have saved the fuel, that is H5 minus H2A, and total available was H4A minus H2A. So that was total difference. So how to determine H4A, H2A, we have. How to determine H5, just put all values here. Effectiveness is given 80%, so it is 0.8. The rest value no, so from here you can determine H5. Q in now will be H3 minus H5, so we have H5 here, so you can determine. And what will the thermal efficiency? Again W net or Q in. Now Q in is less, so when the denominator is less you will get overall good value. So now efficiency has improved 36.9. Previously it was 26.6, and now you have increased it by using the regeneration, because you are utilizing the exhaust heat to preheat the air after compressor. So that is the way how to solve this. So here actually stages has been increased, so you have to if you know how to draw this TS diagram for two-stage compressor, this is compressor increased, then it is intercooled, and ideally you are taking the same you are taking back it to the same temperature as it was inlet of first compressor. So temperature is 300, then you are increasing, ideally you are using the same compressor, mean P2 over P1 and P4 or P3 will be equal. And for you are giving the heat, then H, it is expanded in the turbine, so H6 over H7 and H8 over H9 will be same. Turbine are of same pressure ratio. In between these two turbines you are reheating. So if you have this TS diagram, how to determine, if you have known T1, how to determine T2, that is same as we have done in the first problem. Then this pressure is same, it is constant pressure line, so you know the pressure. T3 you know how to determine. T4, that will be same as this. T2 and T4 will be same because this pressure here is same. After that this T6 and T8 you know, 13, T7, T9 you can find. And when I'm saying you can find the T1, T2, it's mean you can also determine the H1, H2, H3, H4. You can also determine the enthalpies at this point. So this it is being utilized, ideally it is 100% effectiveness. This exhaust is utilized from preheating from here to here, and you are just heating up from H6 H5 to H6 and H7 to H8, and this is ideal, so it will be 2 times. This is ideal. So you have to repeat the things, but looking at this diagram you can find everything. Again, back work ratio, what is the formula? Compressor in or turbine, and thermal efficiency is tool network QN. So this value will be these one after you will calculating. And when there is regeneration, so when regeneration it is 69.6%, it is without regeneration. This question has two part. One is no regeneration, and second is 100% effectiveness. 100% effectiveness mean all the heat that is being wasted, H9 minus H10, is being utilized from heating up from H4 to H5. So 100% heat is transferred, that's why its effectiveness is 100% one. So this is the way how to solve. Rest is the practice. So practice and practice and practice, you can solve the problems. I think this will create no problem for you. So when you have practice, then solving the problem will be less lengthy for you, less time consuming for you. Although the question is a little bit lengthy, but I hope you can do if you have a good practice. Thank you very much. Allah Hafiz.